Hello everyone, welcome back to another video for the series. I'm Inokyu and yes, it's been a while. It's been a while since I uploaded a video in my YouTube channel. And guess what? I even forgot to upload the January newsletter. I'm so sorry about my uh, not being able to focus on this channel. I'm not sure if this is a great excuse, but I was actually quite busy doing schoolworks. Yes, I did know 5 AP courses will give me this much of workloads. Anyways, and I also had other projects that were going on, so yes, I'm so sorry for not being able to focus on this project, on this the problem of the day, this project, and this YouTube channel as well. I am planning to upload more videos frequently. Thank you so much for your support and patience. Now, without further ado, let's start this problem. This problem is 2025 KMO problem number 6, meaning this is the problem that I actually solved during the exam. I was not able to fully solve the problem. I was only able to make partial progress. Uh, I came back home. I was thinking about this problem again because I was like, this problem is it just looks so easy, but we just need to telescope it and we have 3, 4, 5. That's so easy, and I could not understand. I was not able to understand myself that I was not able to solve this problem in the spot. So I came back home, tried this problem again, and guess what? I did solve it. So that's very sad for me, but anyhow, yes, here is the solution. For arbitrary real numbers x sub 1 through x sub 99, such that these are all positive numbers and they are all, what do you call that? Monotonous? I think this is the right term. Determine the minimum value of positive real number c such that the following inequality always holds. This one. Yes. And also, please, one thing to keep in mind. It's been a while since I started studying math again because I was working on other non-math related projects. So if I make any mistake or make mistakes in terminology, please forgive me. Yes. So there are two things that I saw and I see that I think we all can see right now just by looking at this problem. That is 3, oh my goodness, I can't write, 3, 4, 5. And this is very catchy, not because it's increasing by 1, but it's Pythagorean triple. And why is that important? And I think that's very important because we have square roots, and maybe squaring something will cancel things out. And we want to cancel things out and we want to get rid of the square roots because we know that these telescopes, that's very, very pretty. So our only problem is how are we going to get rid of the square roots? I think that is the main part of the problem. So how should we do it? First of all, let's utilize the fact that we have 3, 4, 5, and 3 squared plus 4 squared equals 5 squared. Yes. Let's do it one by one. Oh, wait. Oh, I think it works. Yes, I just saw it, and we can actually group these. I first wanted to group like these two terms because that will give this one. I will just write it. X dot 1 square plus 4 times 4 root x sub 2 minus x sub 1 all the way squared is this thing is equal to, oh wait, it doesn't work. It doesn't work. Oh my goodness, I think just maybe oh, this is not right, I think. Oh wait, we can actually use cosh. We can use cosh. I'm sorry again because it's been a while since I solved this problem and did math again. So if my memory serves me right, wait, Enoch, are you serious? I think I forgot Cauchy-Schwarz inequality. No, no way. This is not true. I forgot. It's this one, right? Yeah, I'm pretty sure it's right. Yes, this is correct. Oh my goodness, I need to review the basics. Okay, so I wanted to use this because let's substitute a as 3, b as root x of 1, and x for y root square sub x of 2 minus x of 1. Then we get plus 1 square. What is this? I'm quite lazy to write them, so I'll just write it like this. We get 3. Oh, this is very, very pretty. This is looking great. Looking great. Yes, the reason. Wait, what? Oh no, sorry, that's my bad. 4 squared. Because a equals 3, b equals 4, x equals root x of 1, y equals root x of 2 minus x of 1. Did I just say? Yes. We know that this is 5. We know they telescope, not telescope, but cancel each other. We get 3 root x of 1 plus 4 root, I wanna write it better, x of 1 plus 4 root x of 2 minus x of 1 is less than or equal to 5 root x of 2. This is looking very good, I think. Okay. Following the same pattern, we intuitively know that this is true without checking. But just to be clear, let's check. 3, 4, that's 5. Yes, and this works. This is 3. And if we generalize this form, we get x of n plus 4 root x of n plus 1. Why can't I write n plus 1 minus x of n less than or equal to 5? And the thing is, can we improve here? Can we improve this inequality? The answer is no. I don't think we can improve this inequality because this equality occurs. Wait, when does equality occur for Cauchy? Oh, I forgot. Because Cauchy is like the special case of Hölder's inequality, and I think it was like something like this. Yes, I think this is right. So the inequality occurs if and only if this is true. Please correct me if I'm wrong. And wait, never mind. I think they can be improved. No, they cannot. Wait, it can be. Sorry, never mind. We don't know if the inequality can be improved or not. Let's just stick with this. Why did I generalize it? We don't have to generalize it now that I think about it. Let's just change it to 99. Because I generalized it because I thought we have infinite terms, but we have only 99 terms. So we don't have to generalize it. Okay, now let's add all these. So we get 3 root square root of x of 1 plus all the way until square root of x of 98 plus okay, x of 1 plus all the way until square root of x of 99 minus x of 98. We know that this is less than or equal to 5 times root x of 2 plus all the way until root x of 99. And this is looking great, I think. Because let's move all of our terms. Let's move all of our terms. Leave this here. Move all these. X of 2 minus x of 1. This problem is so easy. Why did I not write this solution last year? I mean, yes. Let's move this. So we got 2 times x of 2 plus x of wait. 2 plus all the way until root x of. This problem is so clean now that I think about it. There's like it matches perfectly. So that's what we got, and that's the same inequality, except that c equals 2 here. Okay, so we know that c equals 2 works, satisfy. But we just need to check if c can be less than 2. If not, if c cannot be less than 2, then our answer should be c equals 2. Because c equals 2 works. And it just suffices to show, I will write it down. It suffices to show that, therefore, it suffices to show that, I can't write c is greater than or equal to 2. Yeah, let's prove it. Let's prove that when c is less than 2, it doesn't work. How should we prove it? How should I prove it? I think it's better to use this one. The equality occurs if and only if this is true. I'm not sure if it's a to b equals x to y. Let's check this version first. Assume that this is true. Yeah, the equality occurs if and only if. Which one? What is Hurder's inequality? I think based on Hurder's inequality this is true. But we wanna be I think this is right. Let's check it. I think this is right. Yes, this is correct. Anyways, I think we have multiple ways of proving that c must be greater than or equal to 2. One way is to prove that this inequality cannot be improved, meaning it just can't be improved, or when c is less than 2, it doesn't work. So how should we prove it? If C is less than 2, if C is less than 2, then if C is less than 2, wait, let's reverse engineer it. Reverse engineer? No, that's not the correct term. Well, no, let's reverse the whole step. That's the correct term. Let's, okay, say that C is less than 2. So like 1.9 or 1.5, something like that. Then we can add 3. We can add these like to make this term. But notice that it will always be less than this term. So it will be like 3 something plus 4 something, this thing, is less than or equal to C times something plus something is here, this thing, 5 root x of 99. And, oh, I don't think this method works. I'm sorry. Because this will not lead to this separation. This leads to this, but this does not lead to that. We just need to prove that this. Yeah, we just need to prove that this is strict inequality. Because if this is strict, then this value, if this inequality is strict, then this coefficient cannot be less than 5. If it cannot be less than 5, then if we subtract it, then it cannot be less than 2, meaning C must be greater than or equal to 2. So therefore, this is same thing as showing that the inequalities above are strict. I really want to use the fact that these are all not equal to each other. I think we can do it if I know the condition. Yeah, I think this is right. So the equality occurs if and only if this is true. Or does it? Wait, how do I prove that? Cauchy inequalities. Cauchy inequalities are always strict. No matter what, they are always strict, I think. No, not, I mean, yeah, this is strict inequality. Yes, this is strict. Oh my goodness. Yes, we just proved it. Okay, so this is strict inequality because if you just think about the derivation of Cauchy inequality, this actually came from I don't want to expand it, but I have to. Is it 4? Yeah, it came from this. AY minus B. Is it right? So we know that this is strict. This inequality cannot be improved. It cannot be improved. Meaning, because this and this are identical, this cannot be improved. And this are identical, so this cannot be improved. Meaning, these inequalities cannot be improved. Therefore, C must be greater than or equal to 2. And we know that C equals 2 works because, wait, does it work? They work because this works. Because c equals 2 is the result from here. When they are all, so c equals 2 will work if they are all equal to each other. So 3 root x of 1 plus 4 root x of 2 minus x of 1 is equal to 5 root x of 2. And they are all equal to each other, then c equals 2. And that should work. Yeah. Because because this is true. I mean, they're all positive, and yeah. Yeah, that's, and just to prove it, I think the equality occurs if and only if this is true, and there's no restriction that tells that this must be true. Therefore, c can be equal to 2, and I don't need to provide a specific example, because if there's no restrictions, we know that x sub 1 through x sub 99 can be any real number, meaning we can fit the situations given x sub 1. That makes this equation true. Therefore, the positive real number c, the minimum value of positive real number c, is 2. This is the answer. Oh, this took me a while to refresh the old memories and solve this problem. I hope you enjoyed it. If you spot any errors or have any comments or feedback, please feel free to share it in the comment below. I thrive in those situations, I guess. Then thank you so much for watching this video until the end, and see you next time in my next video. Bye.